Way too long. All right. So, yeah. Last time we ended, we were talking about characteristics of the chi-square distribution. And I mentioned it is a sort of a left tail distribution. This is your typical shape. For very small degrees of freedom, it has odd shapes. These two here, the black one and the red and the blue one. But for almost all of them that we're gonna be messing with k degrees of freedom, you have it starts at 0, goes up and then down. It's got a long right tail. Okay, has some characteristics. It's kind of interesting. The mean of a chi-square distribution is the number of degrees of freedom. How weird is that, right? So the mean is the degrees of freedom. The variance is the degrees of freedom minus 1. And the mode, which is the high point, is the degrees of freedom minus 2. So let's take a look for a second at the, let's look at that green curve right there. The green curve is k equals 3. So that's degrees of freedom is 3, right? So that says the mode, the high point there, is at 1, which is k minus 2. The variance is going to be k minus 1, which would be 3. That's kind of weird. And then mean is going to be 4. So the mean of that big, now that's interesting because you see that the mean is 4. Excuse me, I'm sorry, 3 degrees of freedom is 3. So the mean is right here. It seems like there's a lot more to the left of it than to the right of it. The problem is you remember that a mean is sensitive to outliers. And so you have that green curve goes off to infinity. So there's a lot of outliers out there that bring the mean up. This is what I just showed you. It's not symmetric, skewed right, becomes more symmetric as the degrees of freedom increases. And actually, as the degrees of freedom gets really big, it can be approximated with a normal distribution, which we're not going to do. The reason why we're not going to do it is we got calculators and tables and stuff for that make approximating using other distributions like not necessary. Right? Oh, by the way, test corrections you have till Monday. Right? Yes.
Can I swing by your office at like 3 and look at it again? I know you have class at 4, though.
I have class from 2 to 3. At 3 is great.
Oh,
I don't know.
Okay.
I don't have class at 3. Right? There's some that would argue I don't have class anytime. I never have class. Never have class. No, I'm out of hock at 2:50 after I get done with college algebra for business. For business, yes, you may. 3 o'clock's a great time. Right?
Like, I think I'm just gonna look at it today again and ask you all my questions. And
That's good. That's good. I'm down with that. That's great. So in this section, our degrees of freedom. So every degree of freedom defines a new curve, just like the t distribution. And in this section, degrees of freedom are always going to be n minus 1. They will not always be n minus 1. And one case that they're not n minus 1 is in that genetics problem. All right. The fact that it's not symmetric means that we're going to have to compute our critical values in a different way. What does that mean? For a normal and for a t, a critical value, whatever value left, say, 5% in the right tail, the negative of that value left 5% in the left tail. Not anymore. For one thing, all of our chi-squareds are positive. There aren't any negative ones. Okay, number one. Number two, it's not symmetric. So you can't. So we can't take 1.96 negative 1.96 because we got no negatives. Number one. Number two, it's not symmetric. So even if you did have an axis down the middle, it wouldn't have that symmetry that allows those numbers to be negatives of each other. All right. So look here. For degrees of freedom being 12, this is the last one. I think there's chi-square on here. In fact, yes. When it folds the natural way out of the book, the chi-square table is right next to your t table. So here's your tables, right? And if you do this, you turn the tables. Yeah, okay.
That's why I come to this class.
I know. I make up old jokes. They're old on arrival, right? They could be 1 nanosecond old, and they're groaners, man. They're groaners. So you got Z distribution over here, T here, chi-squared here, right? Now the chi-squared is similar to in one way, it's similar to the T table, in one way. And that is you have degrees of freedom down the left. It is very important here, something very, very important that makes the chi-squared different from all the other distributions we've had. You ready? The tables gave you area to the left in normal, in T. Chi-squared tables give you area to the right. To the right. And it says that there. Area to the right of the critical value. So if we want to split 5% into 2 tails, we have to find the area that leaves 2.5% to the right and the area that leaves 97.5% to the right. Now, conveniently, the chi-square table has a second row here that says, if you have, I don't know, yeah, it says area to the right of the critical value, and it's got common areas that you're going to want to the right. So, for example, in this particular one here, I have 12 degrees of freedom. I picked that out of the air. So I go down on my go down in my table, my chi-square table, to the 12 degrees of freedom. So I want the area that leaves 0.025 to the right. So I go up here and I go, okay, 0.025 to the right is right here, down to the 12th degrees of freedom, 23.337. That's where that number comes from. Then I want the one that gives you 97.5% to the right. Because to get 2.5% to the left, I need 97.5% to the right. Okay? And on that same row, the same 12th row, I go to 0.975 to the right, and I get that 4.404. Now, those two have nothing really to do with each other. There's not a good way to get one from the other. All right? So those have to be looked up separately. One isn't the negative of the other. You know, there's not a shortcut. Because if there was a shortcut, I'd be taking it. All right, now, as we did last time, we have a portable chi-square table in our calculator. Calculatus eliminatus, right? So here I got the 23.33. Those are in your notes. Why don't we get the 4.04 value using the equation solver like we did last time? All right. So we go to our calculator and equation solver. Let's see. Last time I knew anything, that was on the math. And then at the very bottom of the math was solver. Okay. Hit enter. Now, I am pretty sure that you two with the TI-83s, you're going to have to hit an up arrow. Okay. And your screens are going to look like the ones in the book. Okay. Your screens are going to look like the ones in the book, which are like the ones on the last slide here. Your screens are going to look like this. So that's one advantage of having a TI-83 is you get screens that match the slides in some cases that the new ones don't. The advantage of having the newer one is that is in most cases a little more convenient. So you go to the equation solver, you hit the up arrow, press up arrow, right? Let's go over here. I mentioned I'm going to get the 4.04 value that we got. So I don't need TCDF. I need chi-squared CDF. So what I do is I position my cursor on that T right there, and I go second distribution, and I want chi-squared CDF, which is choice number 8. Okay, which is choice number 8. All right, and I'm going to want my lower bound to be my x. My upper bound to be infinity. Degrees of freedom, in this case, 12. And paste. Oh, it used to overwrite. Why didn't it do that? Oh, that's a problem. Used to overwrite. Okay, there you go. You have it there. Then, enter. I want from that point to infinity, I'm getting the left bound. So I want from that point to infinity to be 0.975. Right? I go down. I position my cursor on the x equal line. And then I hit solve. And solve is alpha enter. And it's going to think. You see the little circle going up there? So that gives me my 4.04. Right? Your calculator might take another second. All right, 4.04 right there. That's how you find a chi-square. Now, the good thing about this is you're not limited to the values in the right tail that are given on the table. Also, you notice as you go down the table of degrees of freedom, you have all the degrees of freedom from 1 to 25 to 30. Then for some reason, it starts jumping by 10. It goes from 1 to 30, every single degree of freedom. Then it starts jumping by 2. You think it would jump by 5 or 2 or something, right? But it jumps by 10, 10, 10, 10, 10, 10, all the way up to 100. So here, if you needed 78 degrees of freedom, you could just do 78, put 78 in there, right? And that would give it to you, right? Put 78 right here and give that to you. So let me know if you have questions on that. You want me to show it to you on your particular calculator or something. I'd be happy to do that. So that's how you get those values, equation solver. Now, this is our confidence interval for sigma squared, the variance. Confidence interval for sigma squared. This one's going to be different than our confidence intervals heretofore. Up till now, we've had a point estimate in the middle, and then you plugged into a formula for the error term. You got E, right? E. And it was your point estimate plus E, your point estimate minus E. That gave you your two endpoints. Not with this one. Not with this one. You have this on your formula card, I do believe. Let's see. Six. Yes, there they are right there. It's on the formula card. Chapter 7 should be on that formula card, chapter 7. Anyway, it's the one under confidence intervals. On that formula card is chapter 6 because that formula card's older. But look here. Sigma squared is trapped between, this is your left endpoint and that's your right endpoint. The good news is the numerators of those two are the same. So you got n minus 1 times s squared. Where do you get s squared? From your sample. That's your sample variance. And by the way, this is a confidence interval for the variance, not the standard deviation yet. Okay? And so look, you have your sample variance here. Now notice for your left endpoint, since the numerators are the same, for the left endpoint to be less than the right endpoint, look at this. We have chi-squared r. So your right chi-squared value. Now your chi-squared r was this guy over here. So you're going to put your 23 on the left, and you're going to put your 4.04 on the right, in this case. Okay. Yeah. For the confidence interval, we're just going to take this, for the standard deviation, we're just going to take the square root of everything. So this is for standard deviation, but if you take these square roots, that's going to be what we're going to use for the confidence interval. It turns out that mathematically, this is not exactly the best. And the fine print in the book will tell you that. But this is commonly used and it's very close. You take the square roots across the board. So here we have our defensive ends. All right. We're going to find, oh, yes, we may need to make the assumption that the defensive ends are normally distributed. If that's not given to you in the problem, you have to state it. Assume it's normally distributed. You have to make that assumption and then continue. We don't have a procedure right now for when it's not normally distributed. There's a follow-on course to this one that's sort of an intermediate statistics class where we get into what are called non-parametric statistics, right? What are those? Those are procedures. They are procedures that make no assumption on the underlying distribution. See, we're making assumptions on the underlying distribution here. We're assuming the underlying distribution is normal, that the weights of the defensive ends in the NFL are normal, right? That's an assumption. And when it comes to weights, that's usually good if it's the same group of people, you know. So if you took the weights of all females on campus, they would probably be pretty close to normally distributed. The weights of all males on campus, probably pretty much normally distributed. The weights of all men on the men's soccer team, normally distributed, they're probably going to be close. Not in every case, but close, right? So here we're going to construct a 90% confidence interval for the standard deviation of the weight of all defensive ends in the NFL. All right. For some reason, I left writing in here from times gone past. So you got writing on your slide on the slide? Probably. Yes, you do. I see it. All right. Well, it is what it is. Alpha's 0.01, so we're going to want 0.05 in each tail. Half of alpha in each tail. Right? Our degrees of freedom are 39. Now, what you do if you're asked to do this by hand is you go to the table and just use 40 degrees of freedom, okay? That's what you do. So if you're asked to do this by hand, 40, right? If you can use your calculator, you find 39 degrees of freedom. You find out what that is. Okay. These are the two descriptive statistics from before. And so this right over here is our S squared. This is our sample variance right here, 218.1. 218.1. Remember that? It's actually that thing right there. All right. Let's go to our tables for a second. We're going to use 40, like I said, but it's a similar procedure as what we just did with 12 degrees of freedom. You go down to 40. Is down to 40 right here. And with, I want 0.05 in the right tail. And I go to 0.05 column 40. And I get 55.758, which is my chi-squared R right here. Go slide right over on that same line, 55.758. Slide right over to 0.95 in the right tail, and I get 26.509 right there. That's where those two values come from. All right? And you do some calculating. These are our formulas, which you will have. You have those formulas. 39 is n minus 1. This is n minus 1 right here. This is 218.1 is my sample variance. Okay? Sample variance. And then down here are my two chi-squared values. That comes out to this. Remember these. 12.35, 17.91. We're about to do it on the calculator, and we're going to get a slightly different answer. Number one, and we're not going to have as much rounding. Number two, we're going to use a function on your calculator that I actually installed. Should be there, a program for the chi-squared interval. All right, it's a program that I put on. It's not on one of your menus. All right, so it's a program that somebody has out there for the TI-80 3 and 4. All right, so you're going to use S2int program. So here's how to do that. What is going on? Look at all these crazy loopy doopies here. I thought I got rid of those.
They're not on ours.
No, so they printed out okay?
Yeah.
Okay.
Yeah.
Those look like wingdings or something, right? Anyway. Second. Right. So we are going to use, you hit program this time. Oh, I pray it's here. Oh, yes. S2 int. S2. Now there's not, S2 is S squared, right? S squared. I don't know why they didn't put a sigma there, because there is a character on here for sigma, but they put S2 interval, right? You hit enter. And it's going to, you put paste to your home screen, and you're going to run it. Okay? So input stats, I think there's a way to even do the, huh. I don't know if there's a way to do it with the data. I don't know how to make this program take data. But your sample variance, 218.1. Hit enter, enter dummy. N is 40. You don't do N minus 1. Confidence level, 0.9. Hit enter. It is thinking. Notice, look for your little thing up in the corner. It's thinking. Right? You got to remember, these processors and these calculators, they don't even come close to rivaling what's on your phone or what's in a PC, these days, or your laptop, right? I think I told you a while back that I got the Boy Scout Computing Merit Badge in 1976, right? You know what computers were then? The computer I got it on would, I don't think, fit in this room. If it did fit, it was about the size of this room, maybe a little bit bigger. You walked up and down the aisles of the computer. You walked up and down the aisles. They were like refrigerators on the left and right, except they were heating. And then you had a floor. You had a cooled floor. All the big computing facilities, and they still do actually, they have raised floors and they have cooling going under the floor, right? So you can't wick the heat out of that place fast enough, right? Now you got to remember, now there are server farms that are bigger than York. I'm not kidding. Google, Amazon, they have server farms that are miles of buildings. Miles. You know, you talk about the cloud storage, cloud services. They're not up there on some nebulous little thing floating, right? It's on a server somewhere is what it is. So all cloud computing is taken, that's where it comes from. Now look right here. The confidence interval for sigma squared is this. Now I think if you hit enter again, it gives you for sigma. There you go. 12.485 and 8. Those are a little bit different than we got using the table because it uses more precise chi-squared values. Because we only had 40 degrees of freedom. It's using 39, right? So these two would be our answer. Because it asked for sigma, right? And that's what we have right here. Okay. Hello. There you go. Those are a little different than we had before. Let me see here. I think we've already kind of done that. We've already done this. Finding chi-square values on the TI-83, we've already done that. Normal quant. Why is that even here? This was at the end of last chapter. Why is that even there? That's it. That's it for chapter 7. And it escaped me that we were so close to the end of chapter 7, I did not print out chapter 8 slides yet. So what we're going to do, so I'm going to go over here. And I'll at least introduce chapter 8. So I get print. The properties. Two-sided. Hole punch. And we want 4 copies. And where are we sending this? That's going down there. We want to talk a little bit about, oh, that brings me to my next topic. Next topic is, we haven't had a quiz in a while. So, okay, Monday, it looks like the day most of you are going to make corrections on your test. So here's what I'm going to do. We'll have the quiz Wednesday. And it's going to be a quiz computing one or more of the confidence intervals or sample size estimations that we did for chapter 7. So whatever we do for the rest of today and whatever we do on Monday will not be on the quiz. Okay? So quiz on Wednesday, basically over chapter 7. And it will involve, I'll have you computing confidence intervals, possibly finding the chi-square values or t-values, right? Or sample size estimates, right? We only did sample size estimates for 2 situations, right? For population proportion and for population mean when sigma was known. We didn't even do it for population mean when sigma was unknown. So let's do that for next Thursday, or next Wednesday, excuse me. All right. We're going to talk a little bit about hypothesis testing. And the good part is a lot of this is sort of, I hate to say, explaining what a hypothesis test is. Explaining what it is. So this is the only chapter that has a whole section just of introduction before you get to actually doing the hypothesis test, right? Okay. I'm going to hammer some things home with crazy orders of emphasis. One of them is a hypothesis test is a claim, or excuse me, a hypothesis, we'll start with that, a claim regarding a population parameter. A population parameter. What parameters have we had thus far? We've been using mean, proportion, standard deviation, or variance, right? Something like that. But it could be mode, median, all those are population parameters. So any claim regarding a population parameter. Hypothesis test is a procedure for testing that claim about a population based on information drawn from a sample. So a claim regarding population parameter. Here we go. 65, this shows you how old. This shows you how old 65% of Nebraskans favor the repeal of NAFTA. It actually got repealed a couple of years ago, and I think the repeal was a good thing. But NAFTA was the North American Free Trade Association. Now it's USDA, something like that. No, it's USCDA or something like that. It got replaced with another trade agreement. Okay, but this is a claim about a population parameter. Population is Nebraskans. Parameter is P, the proportion. So this is saying that P equals 0.65. That's a claim about a parameter. P, the population proportion, equals 0.65. Now you could also say at least 65%. So that would be P is greater than or equal to 0.65. Because at least is greater than or equal to. Over, P is over or 0.65. P is greater than 0.65 is saying that over 65% support the repeal of NAFTA. Okay. Yeah. Rare event philosophy. Just listen, because I'm going to say a lot more than is written on these slides. So not having the slides is not a huge barrier yet. A couple minutes, I'll run downstairs and get that. Rare event philosophy. When under a certain set of assumptions, we observe something that is very unlikely to occur by chance, there are only two possibilities. One is that we have actually witnessed a rare event. Rare events do occur. They do occur. You know, you say, oh, this twig fell from the tree and it fell right inside this Coca-Cola can. Right? Is that rare? Yeah. How many times does that happen? Right? Well, the thing is, we don't notice all the twigs that didn't fall anywhere or fell on the ground. You know what I'm saying? Of the millions of twigs you've probably seen, that one of them would land in an unusual spot. Rare events do occur. Right? The other thing is, maybe your assumptions are wrong. Right? Maybe our assumptions are wrong. Okay? So, for example, Cassidy would bring into question the fairness of one of my die, right? Right? They have a mind of their own, and they have a striking propensity to land on whatever numbers Cassidy's. Okay, even if she's a low number, it's kind of funny. You know, for a whole semester she was 5 and 6, and that was what all landed on. Right? And then when we get lower numbers, she still. Yeah.
I think we should try it.
Yeah, there you go. Right. Yeah, we'll get there. Yeah. So you've either witnessed a rare event or your assumptions are wrong. That's the rare event philosophy. Which is more likely to have occurred, the rare event or your assumptions being wrong? Probably your assumptions are wrong. The assumption that that's a fair die, probably more likely of it being wrong than me rolling 10 sixes in a row with it. Right? So let's look right here. If we roll a 6 on a die 72 times out of 100, right, then at least one of our assumptions on the fairness of the die is incorrect, or we have witnessed a very rare event. Now, you know how to compute the probability of getting 72 out of 100 sixes. If our probability is 1/6, N is 100, P is 1/6, we're interested in X equals 72, that is this number here. 2.85 times 10 to the minus 34. What is that? That's a decimal place, 33 zeros, and then 285. Right? 285. You would be better, you would have an easier chance of picking a randomly selected lottery number if the number of lottery numbers were the number of molecules in the Milky Way. There are fewer molecules in the Milky Way than 2 times 34, right? You see what I'm saying? Extremely rare, all right? So, although it's possible, the likelihood of us witnessing a rare event this rare is so small that we conclude the underlying assumptions are wrong, that the die is not fair, right? Cassie's going, I told you so. Right? Oh, yeah, okay. Look at this thing here. Let me go down and see if that's off the printer. Because we're going to make, I don't know if you know, this is a bad day to be doing this too, but a crime may have occurred in the stats class. We don't know. But I heard Mars, the suspect here. This is our game of Clue. All right. Okay. All right, here's chapter 8. So, and this is an unfortunate day, because if you read today's York News Times or saw the president's email, yes, we've had some less than seems to have been less than virtuous activity on and around our campus. But okay, in our jurisprudence system, right, we have a claim. The claim is somebody said Mars stole Heidi's calculator. I just would have heard that, you know. Mars, sorry, bro, you're under accusation. You stole, maybe. Oh, I don't know. Okay. So that's our accusation. That's a claim. Now, the claim could be, right? The claim could be he did it and he's guilty, or he didn't do it and he's innocent. That's the truth. Now, we have a trial, and the trial is going to find him either guilty or not guilty. All right? See how that works? So there's what really happened, true or false, and then how the trial comes out. How the trial comes out. All right? Now watch. If he's guilty and the jury finds him guilty, convict the guilty, that's a proper decision, right? Convict the guilty. If he didn't do it and we find him not guilty, so if he didn't do it and he's found not guilty, that's a right decision. You acquitted the innocent. That's a right decision, okay? But there are two kinds of wrong decisions. One is he's not guilty, right? Or he's found not guilty by the jury, but the truth is he really did steal the calculator. So you've acquitted the guilty. We don't like, see, that's an error. That's a wrong decision. And we don't like that error. We don't like to see the guilty people get off, right? But even worse than seeing guilty people get off, our society has placed even a higher priority in not making the other mistake. That he's innocent and found guilty. That's the other wrong decision, because you've convicted the innocent. And in our society, we would rather let a few guilty people go than convict an innocent person. That is our system of jurisprudence, right? So we have this idea of somebody's innocence has to be proven beyond a reasonable doubt. So this is court over here. Mars comes into court. He is assumed innocent walking in our system. By the way, it's not that way everywhere in the world. You hear a lot of guff about our justice system, and it's not perfect. But it's not that way everywhere in the world. Some places you go in the world, you're accused by the authorities. It's your job to prove yourself innocent. Right? You walk in innocent, and it's the prosecution's job to establish that most of the evidence, not just most of the evidence, beyond a reasonable doubt, shows that assumption of innocence is wrong. And that is this is going to be the setup for our hypothesis test. We're going to walk in, there's going to be a claim about a population parameter. Okay? And we're going to walk in with one particular thing assumed correct. And we're going to see if there's enough evidence to reject that assumption of innocence, so to speak. But if the prosecution doesn't bring forth enough evidence to convince jurors beyond a reasonable doubt, then he's found not guilty. By the way, he's not found innocent. In our system, you don't find people innocent. People say that. Oh, he was found innocent. No, he's acquitted. He's found not guilty. Anyway, I'll leave it there. That's the beginning of chapter 8. You got the slides. Have a good weekend. If anybody eats at a cool restaurant, I got to know. My wife and I are going to go out somewhere that we don't know where, but probably somewhere that has a good steak. Right? Where? Laszlo's? Laszlo's. I've never heard of it. Haymarket? Laszlo's. Laszlo's. Thank you. Good. Laszlo's. All right. All right. If we're up to go to Lake tonight, might try that. Thank you. Thank you. See you guys. Have fun.
Thank you, Mr.
Thank you.